Hello. In this video we're going to look at this question here, number 6. A right triangle has a perimeter of 3 meters, its hypotenuse is 130 centimeters. What are the lengths of the other sides? This was a great question because it actually brought out an interesting algebraic technique we haven't talked about. So remember, we're dealing with systems of equations, and we've actually already seen systems in this course. But what we saw were linear systems. Now we have what are called linear quadratic systems. And this presents a new challenge, which I'll show you in 1 second. So I've drawn my diagram here. I've set up my first equation using the perimeter formula. So x plus y plus 130 equals 300, and I've simplified that to x plus y equals 170. And then my second equation I've developed using Pythagoras' theorem. Now, in the past we've dealt with linear systems, so it really didn't matter which equation we used to isolate, and then which equation we substituted into. The algebra would be the same level of difficulty. The interesting thing now is that it actually will matter which of these two equations I choose to isolate for before substitution. And the reason why is because one of them is linear and one of them is not. And that can lead to some interesting algebraic problems. So I've done this 2 ways. On the left I've done it what I would think is the easier way, and that's in blue here. So what I've done in the blue approach is I've isolated for y using equation 1, and then I've called that star, and I've sub star into equation 2. And now I've gone through a little algebra here, and I think it's worth taking a second to make sure you understand this algebra. And then I factored this, and then I get x1 is 120 and x2 is 50, and then I found y in each case. Again, if you get to this step, let's change our colors here for a second. If we get to this step right here and you can't factor this, you can always use the quadratic formula. What some students might do in this problem is they might go and isolate for y in equation 2, in which case they get the square root. So we just follow the same process. We'll call this star, but now we substar into equation 1, and I get this funny equation here. And it presents a new challenge. And actually we need to use an algebraic technique we otherwise haven't seen. To help understand this technique, let's look at this little example problem here on the right. If I wanted to square root a plus 7, so that's root a plus 7 times root a plus 7. And so I multiply root a times root a to get a, root a times 7 to get 7 root a, 7 times root a to get 7 root a, and 7 times 7 to get 49. With a little simplification, I get a plus 14 root a plus 49. So notice, because I have the plus 7 here on the end, when I square it, the square root doesn't go away. And that's the same problem here. Because I have this x right here, if I square both sides, the square root won't go away. So what I first need to do is to subtract x from both sides. And then once I get here, it works out beautifully because I can square the left side, which causes my square root to go away. You can see that right here. And then I square the right side, and that's just good old binomial expansion. So now, with a little bit of algebra, you'll see that I'll get to actually the same quadratic equation that I got to in the other method. And from this point, it's the same solution. So what this problem highlighted in class, which I really liked, was opposed to linear systems, where you really didn't matter which equation you isolated in. When you're dealing with linear quadratic systems, you want to think about which equation is going to be easier to isolate and substitute in. It might be a case that you pick incorrectly and you get to an odd algebraic step like this, which is great. You can scratch your head and figure your way out. Or if you get to the step and you don't know what to do, go back and try the other way. I hope this video helped.